Like, all right. So, can you hear me at the back of the room? Yeah, it's okay. So, I'm Rafael. I work at the Intel Open Source Technology Center. I'm the maintainer of the power management infrastructure in the kernel, and I also maintain the ACPI support subsystem, which is related to power management a bit as well. Today, I'm going to talk about device power management and I'm not following the recommendation to have just a few slides because I'm not sure how many people in the audience are familiar with the device power management in Linux. So I'm going to give an introduction on that, if you don't mind. And then I will talk about the particular problem. So first off, there are sleep states and a working state in Linux. By the way, by Linux, I mean the Linux kernel, which means that for the purpose of this presentation, every operating system based on the Linux kernel is Linux, and with all due respect to differing opinions out there. And so, yeah, okay, so Linux, the Linux kernel, and everything on top of it. So yeah, there are sleep states, and there is the working state. Uh, Sleep states are low power states of the whole system. The entire system has to enter them in an ordered way. Everything is to be suspended and then stay in that state. And then after a while, there's a wake up event. Everything has to be again powered on and resumed and up to the point where it can be used. So sleep states. The working state is everything else, meaning that this is the state in which the system can actually be used. And that's more of a meta state than a particular state, physical state of a system, because there are a lot of different configurations in the working state where some devices may be in use, some may not be in use, and so on. And there are like two boundaries here. Runtime idle is when all of the devices are idle and the whole system is in fact idle, but it is not in a sleep state. And there is runtime active where everything is running or in use. So in this diagram, the width of the pyramid is closely connected to the amount of power consumed by the system in this state. And the distance from here is the time needed to go to the state, or is again loosely connected to the time needed to go from the runtime active configuration to the given state. Yeah. So now we need the sleep states, right? Because you can think that really all the power management could be done in the working state by manipulating the individual devices and CPUs and so on, and we should be able to get to the lowest possible power configuration of the system, the power floor of the system. Okay, but it is not so simple because there are different use cases, and people say, well, I may not want the system say going forward, so I would like to go to a sleep state rather than to try to power manage itself in a runtime fashion. And this photo is a good illustration of this, in my opinion. So you have basically two different ways to get from one side of the river to the other side. One is the bridge here, and the other is the ferry in the foreground. And then they are not very far away from each other, but people choose to use this or that depending on what they do, actually. So, yeah. Sometimes it may be more convenient to go by a ferry, and sometimes it may be more convenient to go by a bridge. Well, that's it. Different use cases, okay? So we use system-wide power management of sleep states for use cases when systems are not going to be used for a long time, and we use the power management in the working state for use cases where the system is generally in use, but some of its components may not be in use. Okay, now, so yeah, we have these two situations. We have the runtime power management or working state power management, and we have system-wide power management. So from the individual device perspective, runtime power management is really simple. So there are two meta states. One is suspended, one is active. Suspended means no accesses from software. So actually, it doesn't mean low power, really. It means the software is not expected to access the device. And it can be in a low power state, it may not be in a low power state. The framework doesn't care. Active means that software can access the device. And so each of, yeah, and there are two transitions defined. One is from suspended to active, and the other is from active to suspended, obviously suspend and resume. There are callbacks related, connected to those. And there is one more operation, which is an idle check, and this is mostly for parents of devices like bridges and USB controllers and things like that. So if you are a bridge, say on a PCI bus, and all of the devices below you have been suspended, then there is a callback that you can use that will be invoked for you, and you can use this callback, say, for scheduling deferred suspend or something else, like you don't have to suspend by using this. So three operations: suspend, resume, and idle check, which may or may not schedule a suspend, or it may suspend immediately, or may do something else. So this is really simple. Now the system-wide power management is a bit more complicated. This actually is two different suspend flows. So one is full suspend and the other is suspend to idle, but the bottom part doesn't matter here. What matters is this, and this, and that. And, these are the device power management operations. So you can see that that there may be up to four different operations for the suspend part and up to four different operations for the resume part. These are the same callbacks, but invoked in a different context a bit. Now you see that there is this runtime power management framework that I was talking about before, and now we have this, and they have different sets of callbacks for each, right? So, but there's more. There's hibernation, which is even more complicated than system suspend. Every transition here. So there are three transitions to get to hibernate the system, and there are two transitions to resume it. I'm not going to go into details on how it works because I will use too much time for that. But in general, it's like the kernel that is hibernating is this thing. It does two transitions. So after the first one, it creates an image. The image is the memory at this point. The image is the memory. Now it has to be saved, so the devices have to be resumed, and the image is saved, and then we can put the system into sleep after saving the image, right? So, and now at this point, the system is very much in a state corresponding to power off or shutdown. Then, when you want to resume it, you need to load a different kernel or a different kernel instance, which then will check if there's an image in storage somewhere, and if there is one, it will carry out an operation analogous to this one, and then it will, after loading the image, obviously, load the image, freeze everything, restore memory, and then it will jump to the previous kernel. So it has to, essentially what this means, it has to overwrite itself with the previous kernel and jump to it, and then carry out the resume. So there is a number of callbacks involved in that. From the device perspective, there are three sets, essentially, in addition to the previous one. A lot of stuff. Okay, now compilation of the code is through, or in layers. So there are layers of code responsible for different things. So the physical device is this, okay? And that there are devices. The device drivers are in principle responsible for handling them, so they should carry out all the operations necessary to, I don't know, suspend, resume, and so on device. But there are cases in which multiple devices are handled in a similar way, like when they are on the same bus type, like PCI. Okay, so there is the PCI standard defines the power management of devices in a standard way. So every driver would have to do it in the same way, which is a waste of code. So there is a different layer of code, which is the bus type layer, and it carries out all of the standard operations needed for power management. And then this is like for PCI and USB and similar. This is what it might. For other bus types, it might not. Okay? So bus types may or may not carry out some power management. And obviously, whatever the bus type layer does has to be consistent with whatever the device driver does. But that's a no-brainer because drivers have to collaborate with the specific bus types, so this actually works out of the box. But there is one more complication. So I said that there are bus types which don't really do any power management by themselves, expecting the drivers to do all of that. But there are things like ACPI, and ACPI defines power management again for devices, and in a standard way or standardized, let us say, way. And we would like to, again, to avoid code duplication by adding a layer of code that will carry out all the ACPI stuff on behalf of device drivers. So that is for this PM domains. And in principle, PM domains can be on top of bus types, and then on top, which are on top of drivers and so on. So the PM domain will carry out power management defined by a standard like ACPI or by a platform like specific I don't know ARM board or something. And then it may collaborate with a bus type if that carries out some power management operations, and it will collaborate with a device driver that usually does power management. Usually, or almost always, when PM domains are used, the bus types don't do anything significant power management wise. So in fact, the PM domain collaborates with the device driver every time directly. Okay, so we can say that we have a bus type or a PM domain and a driver, and these two layers of code actually have to be consistent with each other to support for power management to work. there are cases in which devices have to be in a specific power state for the system to be able to go to sleep. And that power state may not be the same one as for runtime. So that needs to be done. In principle, at least, that needs to be done. The second, the wake-up settings have to be suitable for system sleep. And okay, so today, and I think going to be the case going forward, for runtime PM, we actually allow devices to generate wake-up signals all the time. I mean, if we suspend a device for runtime PM, we will configure it to generate wake-ups if there is input from the else. Like say the keyboard. If it's runtime suspended, it will always be able to wake up, to generate wake-ups. For system sleep, that may not be the case because we may not want the keyboard to wake up the whole system when it is back. So this is this has to be checked again when deciding whether or not the device is suspended. Question 2, analogous. So can we leave devices in suspend when resuming the whole system? Yes, we can, but there are conditions again to be met. And yeah, first of all, if there are any children or consumer devices of the given one, the device must be resumed before them if they are to be resumed. The power state and wake up settings have to be suitable for runtime power management, but that usually is the case. It may not be in some situations. And the final one is interesting because there are some devices that in which really you don't want to resume during the system resume, because if you resume something during system resume, then all of the system has to wait for this one device to resume. So if it takes a lot of time to resume the given device, like a disk, okay, then everybody, and user space in particular, has to wait for this disk to come up, and it takes time. And it's better to just defer the resume of the disk and let user space run, and then like that. Okay, so now the callbacks can be reused. But because of this layer structure of the power management, it may be problematic because the say PM domain has to collaborate with the driver or the other way around, and the reuse of callbacks have to happen at both levels at the same time. That's tricky. Okay, the other things of this. All right, so there are some ways to achieve the goal, which is to optimize suspended resume devices. Currently in the existing code, one of them is called direct complete, which is an optimization that checks the return value of the prepared callback. The prepared callback is the first one invoked during system suspend for every device, and if that returns a positive number, then the PM4 will try to leave the device in suspend, given that it is suspended. Yeah, but it has limitations. It has to be applied to all the hierarchy below the device, as well as for the device itself. For dependency, the reason why is dependencies between devices that have to be met in the resume in the suspend and resume path. So the requirement is that all hierarchy load devices uh, left in suspend for the and yeah, and the way it works, it just keeps all the callbacks for the device except for the last one, and it does that for all of the devices in the part of the hierarchy below. It turns out that this requirement is very strong and actually only causes the live devices to be handled by this. And there are some middle layer middle layer code that does tricks by ignoring the return value from the driver and so on. So there are cases in which that is problematic. Okay, so this is one strategy, and it is used in the kernel by some drivers, by some middle layer code. Okay, the other strategy that was is to use callback wrappers. So there are functions that can be pointed to by device driver callbacks, and they will automatically do all the optimizations that I was talking about. But again, this approach has weaknesses or limitations. If there are, so if the device has children, the children drivers are assumed to use these wrappers. The state and wake up checks that are needed sometimes may be missing for different bus types, different checks, but the wrappers are not specific to any bus types. They are generic, so they have to checks. There is no opt-out for the resume time optimization, so devices will be left in suspend if their state is appropriate for that every time. And the last weakness is that the middle layer callbacks are called by these functions, and that may not work in general. Say it does work for PCI, it does work for the ACI and that whole. Okay. So the new approach to this problem, or how to avoid the weaknesses that I was talking about. There is an idea, or there is some work on going on this. So obviously, the basic observation is that if you have these layers of code, then they have to be consistent. So the layer is between two different layers, two other layers that will be consistent, the one below and the one above. Whatever happens, always is consistent. And to make that happen, the idea is to allow the drivers to tell the power management core and the middle layers what they want to do and what they can, or what they can do. So if the driver tells everybody that, oh, I'm capable of handling a device which is left in suspend during system suspend, then the middle layer can just leave the device in suspend and then don't worry about the driver, right? How to do it? The implementation is to use flags. The driver can set flags for the device to tell other pieces of code what it can do and what it wants to do about or with the driver, the device system resume. And Yeah, and those flags have to be set at the driver probe time. So they are set once and then used going forward. And the driver core will clear them on driver removal. So the driver only needs to set them and then doesn't have to do anything. For no. There are four flags defined today. The first two are for the direct complete optimization I was talking about. So they are this. So the first one is to forbid it if for the cases in which there are the two layers ignoring the current value. Second one is to just tell everybody that the pair is significant and has to be taken into account. So those are like workarounds for bugs in previous code. The other two are more interesting. So the third one is for letting the other layers of code know that the driver is okay with leaving devices in suspend during system-wide transitions. And the other is to tell the other layers of code that the driver wants the device to be left in suspend during system-wide transitions from the sleep state to the working state. Yeah, and then they are defined, they are used somewhat today. So the status of this is, yeah, the first two flags are in use. The second two flags are taken into account by the PM4, the PCI bus type, and the HCPI PM domain. Some drivers use them. And now, yeah, the open part is here. Like, what to the next? So I would like to support the for the generic power domains framework. I have batches I haven't checked if they are if they work correctly with the callback buffers. Yeah, so the open question is really how far we can get with that. So can we just replace everything else? I mean, the direct complete and the callback wrappers with this approach, or do we need to carry all of these optimizations together and try to integrate them? Maybe we need more flags. Maybe it may be beneficial to add support for the existing flags and more bus types and so on. So this is the status today. And that's it for me. So you have questions right now, please ask them. If you don't, but you have them later, then please talk to me. I guess all do. I will. And he will continue with some discussion about the wake up settings.
So I'm completely ignorant of all this. But wouldn't it make sense to define the actual states and run it as a state machine, and then have a driver callback that says, go to this state, and then let the driver figure out how to get there. With the default implementation, if the driver does not just wake it back up, go back to the
Yeah, so
but then driver can implement the state change callback to be more efficient. But I think the biggest problem is you can't change all the code at once, right? There's too many free drivers and buses and what have you out there.
That's present in common cases as well.
Yeah.
Even if it solved the general problem, still this common cases there.
yeah, so for the runtime power management, I was talking about in the beginning, the least the common denominator is the active and suspended meta states, and that's it because power states are different from even in one system there may be multiple buses with different power states. and I would count hours with anything more.
So you now have something like, what is it? 2 runtime calls, a suspend and a zoom, and you have the 8 calls, 4 for a suspend, 4 for a zoom.
System-wide,
System-wide. But can't you build a state machine off of that?
Yeah,
And then tell them, well, we need to go to this particular state.
So there is a problem which I didn't talk about, and I should. And the problem is that, like, there are drivers that don't implement runtime power management, that's the system power management. There are drivers that actually assume the whole way which you receive the device.
But if you do this, if you build a state machine and you just say, well, we are here, we need to go there, you should do it so that you can completely build that using the existing 10 calls as a fallback. Always bringing it back up and then going back down to the existing path. So if they do not implement this state transition callback, 11,
Well,
or however many there are, because I'm sure there's more.
Yeah, there's more.
Yeah, I figured.
Yeah, so, okay, we can talk about this. But I don't think, I don't think.
Yeah, because I have no idea, but the
Yeah,
state
like,
machine
yeah.
seems like, because then the device or the bus knows where it's at and where it needs to go, it might be able to achieve that without waking everything up, going back down again.
So I guess more or less touching there, devices have more than one power state. We have to have 5.
Yeah, but
Today we
if Linux only has to define 4 states, noise might have more. But the fallback doesn't need to.
Well, so this is not about. It's not about power states. This is really not about power states because we always, so for systems sleep, we always put devices to the deepest power state we can. So this is not about power state. This is more about being the configuration from runtime PM or between runtime PM and system sleep.
But
Because-
so the Linux core only has a limited number of states, and we just say, whatever state you're in, we want to go to this one, in suspend, or we want to go from system-wide suspend to runtime. And if that is for you, you know what? Fine.
So currently it's like you have 2 different sets of
Yeah,
2 different state machines. Okay, so if
I
you look at
understand.
this
So
build
build
a
a new state machine that integrates the whole thing.
which is some yeah. Okay,
And so you're already trying to do this,
yeah.
but with fairly limited constraint, because you have these flags that say my runtime spend state is the same as my system.
As my system, yeah.
But there might be a small difference, and then you cannot use this flag. And then the end result of the flag is you still need to go all the way back up and all the way back down.
Yeah.
Whereas if you with state machine, and you say we transition from system-wide to runtime, driver, if it implements this, can do the small change without going all the way back up and all the way down again.
Yeah, that's true, yes. There was a question.
My question, trying to clarify here, what's your ultimate time goals? Do you use the callbacks directly or just to get more flexibility across the
So the design goal is to have one way of doing things. The first, so everybody knows what to do, right? Drivers, integrators, and so on. And I'm not sure if the flags are the ultimate answer at this point, right? So it may be something like along the lines of the speaker is talking about. But I would like to have one common API, for drivers to use, and somehow covering all the legacy as well.
Yeah, so legacy, you would have to implement the new thing with the legacy interface as a fallback
Yeah,
implementation.
yes.
And you can always just bring it all the way back up and then go down. Yeah.
Yes. So that's all for this. Are there any more questions or remarks or thoughts or whatever? Okay.
I have another one. Yeah, I've seen new bus standards where don't necessarily have every policy. I was wondering how maybe it doesn't.
That
Maybe it does.
doesn't a lot because there is a way. There has to be an ordering in which we can suspend all of the devices, which at least one ordering in which we can suspend all the devices and get to the rest, even if the topology is great.
Obviously, you can ask her.
Yeah, yeah. Because if there is no way to do it, we can't really suspend at all. Right, so. There is there are a few references, and I would like you to at least to have a look at the kernel documentation. It is available from kernel R. If you recall the latest HTML documentation, there is a device API document, device power management document. It will be, it is under development, so it only describes the system-wide part right now, but there will be runtime PM part. So this is the ultimate source of information for all that. There are presentations and conferences as well. By the way, will there be a way to put the slides? In
Yeah.
the conference?
Yeah.
Okay, so the links are active, so we can install them. Okay. One more slides, like sponsored by Intel. Okay, that's it.
For your laptop, right?
Okay.
Yeah, you can.